Linear regression is one of the most popular and widely used machine learning algorithms. Understanding the importance of linear regression, in this video we'll properly understand what exactly is linear regression and then have a demo with both R and Python languages. So before we start off with the main part, I'd request you folks to like this video and also hit the subscribe button. So on that note, let's start off with the main topic. So we'll start off by understanding what exactly is a linear line. Now in your high school, you might have worked with this chapter on straight lines. So what exactly is a straight line? Well, it looks something like this, what you see on the screen, isn't it? And now a straight line also has an equation. So it has a mathematical equation and you can represent that using y is equal to mx plus c. So here, what is y, what is x, what is m, and what is c? Let's understand that properly. Y over here is known as the y-intercept. Now, what exactly is y-intercept? Well, so if you put the value of x to be equal to 0, the value which you get is known as the y-intercept. Or in other words, it is basically that particular value where this line, this blue colored line which you see, that particular point on the y-axis where this line intersects it. Now, we have x. What exactly is that? That is known as the x-intercept. So what is x-intercept? Well, it is that point in your coordinate plane where the line intersects the x-axis. So we know what is y-intercept, we know what is x-intercept. Now what is m? M is the slope of the line. And the slope of the line is measured with the x-axis. So again, in your high school, you would have learned about these different trigonometric functions, isn't it? You would have heard about the angle of sine, the angle of cos, and the angle of tan. So if you want to measure the slope of this line, it is basically the tan value or tan theta value. So what is tan theta? It is opposite upon adjacent, or change in y upon change in x. That will give you the slope of this line. So this is just the introductory maths of a linear line. Now, why is this important? Well, this is important because your linear regression model is based on top of a linear line. So here, when we talk about linear regression, this is a predictive model which is based or built on top of the linear line. And we already know that in our linear line, the equation is y is equal to mx plus c. So here, let's actually call this y variable as the dependent variable and this x variable as the independent variable. And I'll give you guys an example to understand this properly. So let's say I'd want to understand the price of a house, or I'd want to predict the price of a house. Now I'd want to do this on the basis of another variable, which is the square feet of the house. So let's say if it's around 1000 square feet, I am looking to buy 1000 square feet and I'd want a standard price for it in a particular area. So currently I live in Bangalore, and let's say there's this place called as Koramangala in Bangalore, and if I'd want to buy a property of around 1000 square foot, then what should be the standard price of the house in this particular area? So for that purpose, what I can do is I can go ahead and build a linear regression model. And over here, the price of the house would be the dependent variable, and I'll denote it with y, and the independent variable or the predictor is the square feet of the house. Now, we are calling these dependent and independent variables because the price of the house is dependent on the square feet of the house. So let's say if I tell someone that the property is of around 2000 square feet, then I'd want them to tell me what is the standard price of the house. Similarly, if I tell them it is around 5000 square feet, what would be the price of the house? So here x, which you see, x is the independent variable, and in this particular example, x would be square feet of the house and y would be the price of the house. So this is how we are using this equation of a straight line to predict something. And also when it comes to linear regression, you'd have to remember that the value which you are predicting or your output or your dependent variable has to be numerical in nature. Now, why is it? Because this is a straight line, obviously. And when you say y is equal to mx plus c, y has to be a numeric value. So this was one such example where we could use linear regression. Now, what we saw was actually the simplest version of linear regression, and obviously it is called a simple linear regression. Now, instead of just one variable, let's say, if we take the same example, if I want to predict the price of the house with respect to, let's say, the square feet of the house, and also I'll add another factor into the picture, and that would be the number of rooms. Now, let's say what I'd want to do is I'd want to predict the price of the house on the basis of the square feet of the house and number of rooms. So here I'm denoting x1 with square feet of the house, and the number of rooms over here, that will be x2. Now what we'll get is a plane. So consider this to be a three-dimensional feature space. In that three-dimensional feature space, obviously you'll have y is what you're trying to predict, x1 and x2. Now, instead of x1 and x2, you can just call that x and z. So in your three-dimensional feature space, you have x1, x2, y. Or if you want to make it easier, or if you want to understand these terms properly, consider this is a x, y, z coordinate plane where x and z are your predictors, or x1, x2 are your predictors, and y is what you are trying to predict or the result. So this is how, when you have more dimensions, when you keep on adding more dimensions, so right now what we have is a linear plane. Now that can be extended to hyperplanes. So this is how linear regression works when you're adding multiple variables into the picture. So this was the theoretical aspect of it. So for now, if it is seeming too complicated, just understand that in linear regression, what you're basically doing is trying to understand the relationship between the independent variable and you also have the dependent variable. And as the independent variable changes, you're trying to understand how the dependent variable also changes. Now that we've understood this, let's go ahead and implement a demo in RStudio on the Boston housing dataset. Right guys, so we opened up RStudio over here. Now, my first task would be to load up the Boston dataset, and this Boston dataset is, it's pre-installed in RStudio. And it comes inside a library. So we have a library called as mass. So if we have to load a library, I'll just write down library. Inside this, I'll give the name of it. I'll just write down mass again. Now that I have loaded this library, I can just have a glance at the dataset. So I'll write down view, and the name of the dataset is Boston. So now let's understand this dataset properly. So I'll give in a question mark over here. Let me write that question mark properly. Let me feed in Boston and let's see what do I get. So this is housing values in suburbs of Boston. So I've got details about the different houses which are present in the suburbs of Boston. And with this demo, what I'd want to do is I'd want to predict the median price range of these houses in Boston with respect to various factors. So all of these columns which you see, these are the factors on the basis of which I am trying to predict this last column. This last column which you see is MEDV. So here if you see MEDV, let me also zoom this a bit. Right. So MEDV here you see that this is the median value of owner occupied homes in $1,000. Now we've got all of the different columns over there. So we've got CRIM, which would stand for per capita crime rate by town. After that, we've got ZN, which is proportion of residential land zones for lots over 25,000 square feet. Then INDES, which is proportion of non-retail businesses acres per town. We've got NOx, which is nitrogen oxides concentration parts per million. RMS, average number of rooms per dwelling. Then we've got age, which is proportion of owner occupied units built prior to 1940. So all of these are the different columns which I have, and on the base of all of these columns, I'd want to predict the price of the house. Now, before I do that, let me start off by doing a bit of exploratory data analysis. So let me just close this for now. So I've had a glance at this data set. What I'd want to do is all of these individual columns which are present, I'd want to analyze them a bit. So for that purpose, what I'll do is I'll again load up a new library called as ggplot2, and with the help of this library, I can perform beautiful visualization. So let's say I'd want to create a histogram for this column called as CRIM. I'll just write down ggplot, and then I need to map something on the data layer. So here, data is basically the data set on which I'm working on. And the data set is Boston. So let me just write down Boston over here. And AES is the aesthetic. So from this data layer, I need to map something onto the X aesthetic. And since I want to create a histogram is normally present on the x-axis. So what I'll do is I want to analyze, let's say, this age column. So what I'll do is I will map the age column onto the X aesthetic, and since I want to create a histogram, I will just write down geom histogram over here, and this is what I get. Now let me zoom this. So when I zoom this, this is what I get. So let me also go back and understand what exactly is the age column. So if you see this, your age column tells you proportion of owner occupied units built prior to 1940. So this is what I am getting over here. Now again, similarly, let's say I'd want to understand the nitrogen oxides concentration. So if I'd want to understand the nitrogen oxides concentration, I'll just remove this, and inside this I'll put in NOx, and this is what I get. So here, this is nitrogen oxides concentration, parts per 10 million. So when we say parts per 10 million, let me again zoom this properly so you guys can see this, right? So most of these houses, you will see that we have around 0.45-ish, a concentration of nitrogen per 10 million, right? So this is quite an interesting observation over here. So now this is the plot. If I want to add some color to this, that is something which also can be done. So this is the command over here. Inside this command, what I'll do is, so I have something called as fill. I'll set fill is equal to green. Now when I do that, you will see that automatically the color of this histogram has changed to green. Now I can also add a boundary color. To add the boundary color, I have another attribute called as COL, and for COL, let me say, let me just give in dark green over here. I'll write down dark green, and this is what I get. So I have created this beautiful histogram for this particular column, which is NOx. So I can do all of these basic exploratory data analysis. I can perform visualization on this. Similarly, let's say from this entire, so I've got 506 entries over here, or 506 different houses over here. Now what I'd want to do is I'd want to extract all of those records where, so let's say if I'd want to check all of these, I'd want to check all of those records where the NOx percentage is greater than, let's say, 0.7, right? So for that, now this is a bit of data manipulation, and for that purpose I have a library called as deployer. So I'll just write down library of deployer. I've loaded it, and inside the deployer library I have the filter method. Now first I'll give in the name of the data frame, which is Boston. From this Boston data frame, what I'd want to do is I'd want to extract all of those records or all of those houses where the NOx value is greater than 0.7. So I'll just give in the condition NOx is greater than 0.7, and I'll go ahead and store this in, let's say, NOx 0. Let me just write in NOx great. Now view of NOx great, and let's see what do we get over here. So in this new data frame which I've created from the original Boston data frame, if you look at this NOx column, you will see that all of the values are greater than 0.7. Right, so this is quite interesting. So here, out of the 506 houses which we have, 61 houses there, the nitrogen levels are greater than 0.7. This is quite interesting. And this is the median price range of the houses where the NOx value is greater than 0.7. Quite an interesting observation, isn't it? Similarly, what I want to do is, let's see what is the tax column about. So tax states that full value property tax rate per $10,000 doesn't really give me much information. Then we have RAD as index of accessibility to radial highways, weighted mean of distances to 5 Boston employment centers. Then we've got Let's check RM. So RM tells me average number of rooms per dwelling. Now I'd want to check this. So here what I'll do is, again, I'll create a histogram for RM, ggplot data, and for this I will map in RM data is equal to RM, and then I would need the aesthetic layer, and for this I will map RM onto this. And since I need to create a histogram, I'll just write down geom histogram over here. So seems like there is an error. So inside data, I would actually need to pass in Boston. This wouldn't be RM. Now when I hit enter, you will see that I get this beautiful histogram. And let me zoom this over here. And you would see that we've got this beautiful plot over here. And this would tell you that out of all the houses, most of the houses, they have around 6 to 7 rooms, right? So if you see this, the peak, it sort of starts around 5.5-ish and it drops at 6.5 or near to 7. Now, I'd want to have a glance at all of those houses where I have, let's say, around greater than 6 rooms. Let me give in that condition. So what I'll do is I'll give in a new condition over here. So from all of this different houses which I have, from that I'd want to extract only those houses where the number of rooms are greater than 6. So I'll give in this condition filter where RM is greater than 6, and I'll store this in RM6. View of RM6, and let me see what do I get. Here, if I show you this particular column over here, so out of the 506 records, you will see that 333 records, the RM value is greater than 6. So in all of these different house samples, you will see that the number of rooms are greater than 6. So all of this different information I can find out from this. Now that I have done the basic data analysis, I can go to the model building process. Now, in any data science lifecycle, it is important that you understand your data first, understand all of the variables first, and then go ahead and build your model. So that is why we had done the basic pre-processing. Now that's done, I can go ahead and build the linear regression model. Now to build this model, I have this method called as LM. So LM stands for linear model over here, and with the help of this, I can create a linear regression model. Now, the first parameter is a formula. What does that formula take in? It takes in the dependent variable and whatever independent variables we have. So my dependent variable over here is MEDV, which is the average price of the house, and that is what I'd want to predict. So here Y is equal to MEDV. Then I just given this tilde symbol, which you can consider this to be sort of equal to. So MEDV is, then I need to give in your independent variable. Now I'd want to understand what is the price range, or what is the median price range of these houses with respect to, let's say, the RM value. Let's say with respect to the number of rooms, I'll just give in RM over here. Now both of these columns, where are they coming from? They are coming from the Boston Dataset. So I'll just set data is equal to Boston. Now I'll go ahead and store this in, let's say, mod 1. Now let me print out mod 1 for you guys. So this is the linear regression model which I've built. And since linear regression is nothing but your equation of linear line, which is y is equal to mx plus c. Here y is MEDV, x is RM. Now what is m, what is c? So here m, this is the value 9.102. So 9.102 is your slope. Now you can also take it this way. So with every 1 unit change in x1 value, there is 9.102 units change in MEDV if your constant is 0. So here this is your constant, and this is equal to minus 34.671. Alright, so we've built this model. Now after this, I also need to predict values, isn't it? So to predict the values, I have something called as the predict method. Inside this, I'll just pass in the model which I've just built, which is equal to mod 1. And I'd want to predict in, obviously, on some top of the same data set, which is Boston. So let me write in Boston over here, and when I hit enter, you will see that I've got all of these values. What are these values? These are the predicted values of the houses. So here you will see that for this record, the first record, the actual value is 24. The model which I've built, it has predicted the average price to be 25. Close enough. Here, the average price is 21. It has been predicted 23. It's a bit far off. Now, also you'd have to understand that this is in thousands of dollars, right? You are not selling a house for just $24. So that's $24,000, right? If I'm not wrong over here, let me check this again, right? So median value of owner occupied homes in $1,000. And that's correct. All right. So now I'd want to have a glance at this. So have I stored it somewhere? I have not. Now what I'll do is I'll take this command and I'll store it in, let's say, Boston predicted. And let me have a glance at this view of Boston predicted. And okay, so this is what we actually have over here. But what I'd want to do is I'd want to combine this and this. So I'll just write down cbind, and I'd want to combine the actual prices with the predicted prices. The actual prices are present in this column, MEDV column of Boston. So I'll write down Boston $MEDV, and the predicted values are present in Boston predicted. Let me write it properly. Boston predicted, and let me hit enter. Now let me store this, and I'll have something called as a full house because I've recently started playing poker. And since this is the actual values, I'll give the name of the column as actual, and since these are predicted values, I'll give the name of the column as predicted. Let me hit enter. The view of full house, and this is what we get. So these are the actual prices of the houses, and these are the predicted prices of the houses. Now you'll see that there's a difference in prediction, and that difference between the actual values and the predicted values is what is known as the error in prediction. And your best model needs to have as less error as possible. So that is how you get the optimal model. Whichever model has the least error, that would be your best fit model. Now, how do we find that? Well, for that purpose, let me just go ahead and calculate the error. So here, this is actually a matrix. Let me convert that to a data frame first. So I'll write down as.data frame full house, and I'll store it back into full house. Now that I have this, I'll have full house dollar actual minus full house dollar predicted. So actual minus predicted, this will give me the error in prediction. Let me take this properly over here, and I'll store this in a new object, and I'll call that as, let's say, error 1. Now I'd want to combine error 1 back to this data frame. So again, I'll use cbind. Inside this, the first parameter would obviously be full house, and along with full house, I'll have, what do I need to have? I need to have error 1, and I should store it back to full house, and this is what I get. The actual values, the predicted values, and the error in prediction. And now, so error seems like I've not calculated this properly, so I have written over here actual minus actual. So let me redo that. Let me change it to predicted, and I'll store it back in error 1. And now cbind full house error 1, I'll do this. So here, or let me just store it in full house 1. All right. So now that I have this extra column, what I can do is I can just drop it from here. So for that purpose, I'll again use deployer, which I have already loaded. I'll write down Boston, and from this I'll use the filter method, and inside the filter method, I actually need to use the select method over here. Select, I'll give in all of the names of the columns, and the names of the columns are actual, I would need predicted, and I would need error 1, Let me store this in full house, and let's see, actual doesn't exist. Let me go ahead and remove these over here. I have actual, so this is also full house, this is not Boston. Let me change it to full house. I have actual, I have predicted, I have error 1. So from this full house data frame, I need to select these, error 1 at location 3s and 4. Yes, correct. So what I'd want to do is I'd want to select only the actual and the predicted. I'll also remove error 1 from over here. I'll store it back. Right. So now that we have this, now I can perform the same operation properly. So I'll write down full house $actual minus full house $predicted, and I'll go ahead, copy this, paste it over here. Once I do this, what I'd want to do is I'll store it back in something called as error final, and I'll combine this with error final. So C bind of full house, and I'm combining it with error final. I shall store it back to full house, and this is what we have. So here we have the actual prices, the predicted prices, and the error in prediction. And now if I want to somehow find out the average prediction over here, what I can do is I have something called as root mean square error. Let me write that down over here, root mean square error, which would mean that this error which you see, first you take the square of it, then you take the mean of it, then you take the root of it. So if you have to compare the accuracy or the optimal level of your two models, then whichever model will have the lower value of root mean square error, that would be better. So here what I'll do is I'll perform root mean square error. So for that purpose, I would first need to take the error. So full house $final error, and since I want the square of it, I'll do this. Now since I have the square, what I want is also the mean of it. So again, I'll copy this, I'll paste it over here, and I'll get the mean of it. Now, after I get the mean, I would also need the square root of it. So let me copy this entire thing, I'll paste it over here, and I will just write down SQRT. Let me write that down properly over here. So I have root mean square error, and this is the result which I get. So I have a value of 6.603, which is the root mean square error of the model which I've just built. And let me go ahead and store this in something called as RMSE1. So till now we've built a model directly on top of the data set. But the problem with that is what we're doing is we are overfitting the model. Now what exactly is overfitting? Well, if we fit the entire model on top of a singular data without testing if the model is working properly, that is known as overfitting. So let me give you guys an example. And now let's say you guys are giving an exam, and in that exam somehow let's say the question paper leaks. So let's say your friend comes up to you and says, hey, we've got these 5 questions which will definitely come in the exam. So let's say the exam is of only 5 questions and you already know which of those 5 questions are going to come in the exam. So now, since you already have the leaked question paper, and if you learn all of those 5 questions properly, and now if you go and sit in the exam and if the same questions appear, well, you'll obviously get full marks out of them. But what if that information was incorrect? Now, let's just assume that somehow the paper got leaked, but maybe all of those 5 questions are incorrect. Those are not the questions which you'll be getting in the exam. But what happened was you prepared for only of those 5 questions instead of preparing the entire syllabus. Now when you appear for the test, you'll get 0 out of 5 instead of getting 5 out of 5. So that is why it is always important to divide your data into training and testing sets. Now what you do is you build your model on top of the train set and then you test it on top of the test set, obviously. So in this way, what you're avoiding is overfitting of your model. Now, once that is clear, my idea or my aim right now would be to divide this entire data set into training and testing sets. And normally we take a 65-35 split or a 70-30 split. So this is normally the norm, but then again, that is totally trial and error. So what I'll do is I'll divide this into two separate sets. One would be my training set, another would be my testing set, and I'll be building my model on top of the training set and I'll be testing it on top of the test set, obviously. And for that purpose, I would need a library called as CA tools. Let me just go ahead and load that. I'll just write down library of CA tools, and this will provide me a function called as sample.split. Let me write it down properly over here. So this is the function. Now, as you see over here, this takes in two parameters. The first parameter is basically the column which I'd want to split, and the column is this one, MEDV column, and then I'd want to split it in a ratio of 65-35. For this, I'll just write down Boston, and then I need to give him the name of the column which is equal to MEDV. After that, I have a parameter called as split ratio, and inside split ratio, I'll give in a value of 0.65. Now, what this means is, out of this entire data frame, 65% of the records will get a true value and the rest of the 35% of the records will get a false value. Now, I'll go ahead and store this in a new object and I'll call that as sample tag. Let me just print out sample tag for you guys so that you can understand what is present over here. You just see that these are just a bunch of true and false values. And by default, you'll have 65% of the records to have true value. The rest of the 35% of the records to have the false value. Now, I'd want to only extract the records. I don't want the true and false values. So for this, what I'll do is I have a method called as subset. Now, the subset function obviously helps us to create a subset from the original data frame. So what is my original data frame over here? That is this Boston data frame. I'll go ahead and give in the name of the data frame, which is Boston. Now, from this, what I'd want to do is I'd want to extract all of those records where the sample tag or the value in the sample tag is equal to true, which would mean that I'm extracting the 65% of the records from this entire data frame, and I'll go ahead and store it in a new object and I'll call that object as train. Similarly, so here as you see, my original data frame had 506 records. Here on the right side, if you look at this environment pane, global environment pane, you will see that I've created a new data set called as train, and it has 353 observations. So of the 506 observations, 353 have been recorded or have been stored into the train set. Similarly, from the entire Boston data set, what I'd want to do is I'd want to extract only those records where the sample tab is equal to false. So I'll extract all of them and I will store that in something called as test. Again, here you shall see that I have 153 records in this test set. Now, let me have a glance at the training set and the testing set. So view of train, and this is what I get. Similarly, I'll write down view. Inside this, I'll give in test, and this is what I get. So from the Boston data set, I have been able to create two subsets, which are the training subset and the testing subset. And now I would have to build the model on top of the training set, and we already know what are we supposed to do. So here I have a method called as LM. So I'll just write down LM, which would stand for linear model. Now in this, as you see, I would need to give in the formula. So in the formula, I would have to first give in the dependent variable, and then after that I would have to give in all of the independent variables. So here the dependent variable is the MEDV column. So I'll write down MEDV and then I'll give in the still symbol. And then I'll follow it up with the independent variable. So again, I'll take the RM, which is the number of rooms over here, as the independent column. And this time, this formula or these data points are coming from the train set. Right? So I'm taking this only from the train set, not the entire Boston data frame. This will give me a model. Let me call it as mod. I'll take it as mod 2. Now let me print out mod 2 for you guys. So here, this is the LM formula which I've applied. Here I have the RM value. So this would mean that by 1 unit increase in the RM value, there is 9.695 units increase in the MEDV value. And we have the intercept over here, which is minus 38. After this, what I want to do is, I can just go ahead and predict these values on top of the test set. So if I am going ahead and predicting the values, I would obviously need the predict function. I'll write predict, and inside this, I would need to pass in the model which I've just created, which is mod2. Then going ahead, the data which I'll be using is the test set. So obviously I have trained the model on top of the training set. Now it's time to test it on top of this test subset. I'll go ahead and I shall store it in something called as result MEDV. Now let me print out result MEDV for you guys. So these are all of the predicted values. Now I have to compare the actual values with the predicted values. So where are the actual values? Well, you can find the actual values in the test set. So in the test set, you see this MEDV column. These are all of the actual values. This value which you see 24.0, for that we have predicted 25. You have this value 33, for that we have predicted 29. Similarly, you have 28 over here, for that we have predicted 24. Now, I'd have to combine these actual values with the predicted values. Let me go ahead and do that. So I shall use a method called as cbind, and here I'll give in the name of the first column as actual, and I am getting those values from test $MEDV, and the predicted values are coming from result MEDV. This again I will name as predicted, and I shall go ahead and store it in a new object. I shall call that new object as full house 2. Let me have a glance at this view of full house 2. So here I have the actual values, here I have the predicted values. Now I need to find out the error. And before I do that, I need to convert this matrix into a data frame. So as dot data frame, inside this, I shall pass in full house 2, and then I shall go ahead and store it in full house 2 again. Now need to find the error. Full house 2 $actual minus full house 2 $predicted. And let me copy this entire thing over here and paste it inside this. And I shall store it in something called as error2. Now I can combine error2 with this full house 2. cbind of full house 2 with error2, and again the result would be stored in full house 2. So here I have the actual values, the predicted values, and the error in prediction. Now if I am supposed to find out an average error for this entire model or the average accuracy, I have something called as root mean square error, and we know that lower the value of RMSE, the better the model is. So here I already have the error. So let me take full house 2. The name of the column is error2. I need to start off by taking the square of this. Okay, let's do that. So I have taken the square of this. After taking the square, what do I need to do? So it is root mean square. So I need to take the mean of it. And after I take the mean of it, I would also need the square root. Let me cut this out from here and paste it inside this. I would also need square root. So root mean square error, and let's see what do we get. So we get 7.06. This is interesting. I'll go ahead and store this in RMSE2. Now what I want to do is I'd want to add another independent variable into this. So I'm just throwing one more predictor into this model, and I'll see if the RMSE value reduces or if it increases. So I have this over here. Now what I'd want to do is I'd want to understand the price of the MEDV or the price of the house with respect to the number of rooms and also the Knox value over here. So this time I shall create a new model. I don't have to divide my training and testing set again because I shall be using the same train and test. It's just that I will have a new model where I have new independent variables or a new composition of independent variables. So in the earlier model, we only had this RM value as the independent variable. So we are building a new model. In this, my dependent variable would be MEDV. Now after this, I'm using RM as one independent variable. And after this, I'm also using Knox as another independent variable over here. Now, these both values are coming from my training set. So data is equal to train. And I'll go ahead and store this in a new object. I'll call this as mod3. Now, when I print out mod3 over here, you'll see this formula. Here, you have formula as MEDV RM plus Knox. Now, you'd have to understand over here that whenever we are building the linear regression model, the model assumes that the independent variables, obviously, they are independent of each other, which would mean that RM does not influence Knox and Knox does not influence RM. Which would mean that if I'm trying to predict the price of a house with respect to RM, then NOx does not influence it, right? So you would have to understand this properly over here. And also there is one more assumption. So the assumption is there is a linear relationship between your independent variables and the predictor. And now what happens is whenever there's a lot of collinearity, what exactly is collinearity? So let's say if there is collinearity between RM and Knox, that would mean that, well, you can sort of assume that both of them are sort of saying the same thing. And both of them are sort of saying the same thing. It is not really viable to include both the variables into your equation. What you can do is you can use one of them into the equation. So that is why it is better to have different types of independent variables in your data to reduce collinearity and also to get the optimal result. So here it seems that there is a linear relationship sort of between RM and MEDV, and there is an inverse relationship between Knox and MEDV, which would mean, that is sort of intuitive, isn't it? If the nitrogen levels increases, the price of the house would increase. If the number of rooms would increase, the price of the house would increase, right? So I'll repeat it again. If the number of rooms increase, the price of the house would increase. But if nitrogen levels increase, or what exactly is this? I believe this is nitrogen only, if I'm not wrong. So this is nitrogen oxide concentration. So if the nitrogen oxide concentrations increase, then the house price would decrease because probably you cannot habitat over there that easily. So you would have these sort of problems over there. And now, when I've built this model, I want to compare the accuracy of this model with my earlier model, which was mod 2. So again, for that, what I'll do is I'll use the predict method. Inside the predict method, again, I need to take in mod 3. Now, new data is obviously the test data, and I shall go ahead and store this in, let me call this MEDV result. So just the opposite of the earlier one. Now that I have this, what I'd want to do is I'd want to combine the actual values with the predicted values again. So the actual values are obviously present in test $MEDV and the predicted values are present in MEDV result. This I'm going to name as actual, and this I shall name it as predicted. Now I will go ahead and store this in full house 3. And let me have a glance at this view of full house 3. And as you see, I've got the actual values, I've got the predicted values over here. So this is the test set. This is what I have over here. Now, here if you see, look at the value, 24 is the actual value. The predicted value is 25. Similarly, the actual value is 33, predicted value is 30, the actual value is 28, the predicted value is 25. Obviously, there is error in prediction. Let's calculate that error right now. So to calculate the error, I again need to convert this into a data frame. So as dot data frame, what do I need to do over here? I just need to pass in full house 3 over here and store it back to full house 3. Now that this is done, let me go ahead and calculate the error. So full house $3 actual minus full house $3 predicted. Let me copy this, paste this inside this, and cut this out over here. So actual minus predicted, this will give me the error, and I shall store that in error 3. Now I can go ahead and combine this error with the actual values again. So here I shall have full house $3. I actually need to combine this, so I would need to use cbind over here. Original values are present in full house 3, and I need to combine the error, which is error 3, and I will store it back into full house 3. I've got the error column as well. So now that I have the error column, I can again go back, find out the RMSE value. What exactly is RMSE? RMSE stands for root mean square error. So let me go ahead and calculate the square first. Full house 3, I'll give in a square over here. Let me copy this, paste it inside this. Let me cut this out over here. Then I would need the mean of it. Let me cut this out, paste it over here, and I would also need the square root of it. So root mean square error. So here this is actually full house $3 error 3 power 2. Now let me hit enter. I have a value of 6.79. Now let me compare this with RMSE2. So in RMSE2 we had only one independent variable, which was of RM, or the number of rooms. Now here we are taking the mixture or composition of two variables, which is of NOx, which is the nitrogen oxide concentration levels, and I also have the number of rooms. So it would seem that this model which I have built is much better than the earlier model. I wouldn't say much better, but slightly better. So, this is the RMSE value for the model which I've built. So obviously lower the RMSE value, better your model, because RMSE stands for root mean square error, which again, if you'd want to intuitively understand this, lower the error value, better the model it is. So this is how we can create different models with permutations and combinations of all of the independent variables, and we can come out with the optimal model. Now we'll be implementing linear regression with Python. So for that purpose, I have opened up Jupyter Notebook over here, and in this I have a kernel opened up for Python. Now we'll be implementing this linear regression algorithm on top of a dataset called as Iris. So to load that dataset, I would need the pandas library. So my first task would be to go ahead and load that library. So here I shall just write down import pandas as PD. Let me run this. So after loading this, what I would have to do is go ahead and load the file. Here I shall write down pd.read_csv. So this is the method with the help of which we can load a CSV file with the help of the pandas library. So here pd.read_csv, the name of the file is iris. So I shall give in the complete name, which is iris.csv, and I shall store it in a new object, and I shall call that object as iris as well. I have loaded this. Now let me have a glance at the first few records of this data frame. So as we had the head method in our studio or our programming language, similarly we have the head method in Python as well. So here I shall write down iris.head, and by default I'll get the first 5 records in this data frame. And as you see, I've got all of these different columns over here. I've got sepal length, sepal width, petal length, petal width, and species. So this iris flower basically has 3 different species, which are Setosa, versicolor, and virginica, and I have the different features of these different species. So these features are the sepal length, sepal width, petal length, and petal width respectively. Now what I'd want to do is I'd want to understand the relationship between sepal length and petal length. And for that purpose, I'll be building a linear regression model, and here my independent variable would be sepal length and the dependent variable would be petal length. So here I'm basically trying to understand how does petal length vary with respect to sepal length. Now for that I'd have to extract the predictor and also the dependent variable. So predictor, which is sepal length, let me go ahead and store that in a value called as x. So here I'll have a data frame. The name of the data frame is iris. Obviously, here I'll give in two braces, and the name of the column is sepal underscore length. So from this iris data frame, I'm extracting this sepal length and I'm storing it in this object called as x. Similarly, I'll create a new variable called as y, and in y I'll be storing petal length, which would be the dependent variable. So I'll have iris. Let me write down petal length over here. So now that I have the dependent variable and the independent variable, now it's time to divide this data set into training and testing sets as well. So to divide this into training and testing sets, I would need something else from the sklearn library. So sklearn is the scikit-learn library, which is normally used for machine learning purposes and a bit of computation. So using this library, what I'll do is I have something called as the train test split method. And using the method, I will divide this into training set and the testing set. From, let me write it down properly over here, from sklearn dot model selection import train test split. So now that I have imported train test split, what do I need to do? So let me write down train test split over here again. I'll pass in the predictor and the dependent variable. So x, comma y, and I need to set the test size as well. So I'll give in the test size as 0.3, which would mean that 30% of the records should be in the testing set and the rest of the 70% of the records should be in the training set. Now this will give me 4 outputs. So I shall go ahead and store them in something called as xtrain, xtest, ytrain, and ytest. So I have xtrain, xtest, ytrain, and ytest. So xtrain is the training set of the independent variable. Xtest is the testing set of the independent variable. Then I have ytrain, which is the training set of the dependent variable. And then I have the ytest value, which is the testing set of the dependent variable. So I'll get all of these 4 outputs. Now from these 4 outputs, we have already seen that if I'd want to build a model, I'd want to build it on top of the training set. And if I'd have to predict something, I'd want to predict it on top of the test set. So now I would need the linear regression model. So again, from sklearn, let me go ahead and import linear regression. So this time I'll write down from sklearn dot linear model import linear regression. So now that I have imported linear regression, let me just go ahead and create an instance of it. Here I shall write LR is equal to linear regression, which would mean that I am creating an instance of this. So now that I have created this instance, I would have to go ahead and fit this on top of the train set. So I will write lr.fit, and my train set comprises of the xtrain value and the ytrain value. Xtrain, comma, ytrain, and I have fit this model successfully on top of the train set. Now it's time to predict the values. So to predict the values, I'll use the predict method, and inside this I will give in xtest. And I would have to type lr.predict actually, and when I give an lr.predict, you will see that these are all of the predicted values. Let me store the predicted values in a new object, and I'll call that new object as ypred. So now I've got my actual values which are there in ytest and the predicted values which are there in ypred. So let me just show you a glimpse of both of them. I'll have ytest.head. Then I'll have ypred, and I'll give in 0 to 5. So here, as you see, these are the actual values, these are the predicted values. So if the actual value of petal length was 4.1, my model predicted that the value is 3.35. Similarly, when the actual value is 1.7, the model predicted that the value is 3.53. Here you see that the actual value was 5.3, the model predicted that it was 5.001. So we have the actual values and the predicted values. Now we'd have to find out the mean squared error. So here I don't have to separately find out the error by subtracting the actual value minus the predicted value. I already have a predefined method called as mean squared error in the sklearn library, and I can just go ahead and use that. So here I will write from sklearn.metrics. So from sklearn.metrics, I would have to import something called as mean squared error. And now that I have imported this, let me use this over here, and inside this I'll just pass in the actual values which are there in y-test, and then I can pass in the predicted values which are there in y-pred. Now when I hit enter, you will see that I get this value of 0.70, which is the mean squared error of the model which I've built. So folks, this is how we can also build a linear regression model in Python. Thank you.